Now we're talking about stuff like self-driving cars. Juan talked about that. As a matter of fact, they are a thing now. And so many other things that happened in the last few years, digital assistants that are voice controlled in our phones, they feel like they happened overnight. They felt kind of sudden. But they're not sudden, or they didn't happen overnight. They have a long story. They come from the 50s, actually. They come from the 1950s, and that story impacted us all. It's an interesting story. It came from a dream and a war, so to say. The dream is also the title of this presentation. It's this idea that computers can think, maybe in the same sense that you and I think. And the war was the war between two very different ways to get there. Two camps, two factions that had this conflict of ideas about how do we build machines that think. One of the two factions was called the symbolists. And the idea of the symbolists is basically thinking is, they said, is manipulating symbols. So for example, language is manipulating words, sentences. Vision is manipulating shapes. So let's build systems with software that manipulate symbols. And eventually, they will be intelligent. So we're talking about coding intelligence, bottom up. So first, you want to build computer vision. You start by building a machine that recognizes very simple shapes, circles, squares. Then you build upon it, and so on and so on. And finally, you have intelligence, which kind of sounds, it sounds kind of naive today. But back then, computers were a very new thing. So who knew what they could be capable of with the right software? One thing was clear, you couldn't get there with machine language. That's all they had. And they needed better languages, so the symbolists set out to write better languages. This gentleman was one of the foremost symbolists, and he decided to write a language to achieve, eventually, intelligence. And that was one of the very first, I think the second higher level language that gained any traction, and it was Lisp. And it did impact us, because Lisp was the inspiration for the core of Ruby. I went straight to the source to validate that. Thank you, Matsumoto-san. He wasn't the most important symbolist anyway. The most important symbolist was this guy. Marvin Minsky, big brain, great inventor, very respected academic. He got the research money, he got the street cred, he got it all, and he devoted his entire life to building symbolic AI. He was the thought leader of the symbolists. He worked at the MIT through his lifetime, building things like this robot who could recognize blocks, stack them, and so on. But there was another camp that was a little bit by the side. They were the underdogs, so to say. They didn't have as much research money or street cred as Marvin Minsky. They were called the connectionists. And their idea was very different. They didn't set out to build intelligence by coding it top to bottom. What they said was, there is one intelligent machine that we know. That's all we have. It's the brain, right? So they said, good, let's build a brain. Intelligence will follow. And we don't know that much about the brain, but we do know a few things. One is that the brain is made out of neurons that look pretty much like this. And each neuron, if you look closely, has inputs called the dendrites, and one output, essentially, called an axon. And simplifying wildly, the way that a neuron works is that if you get enough accumulated signal, electrochemical signals, from the dendrites, then the neuron sends a signal on the axon. The neuron fires, in neurological terms. And then the axon is connected to other neurons through connections called the synapses, so you get this chain reaction of sort. And the connection is said, good, let's build a neuron. In particular, this guy set out to build a neuron. He was kind of like the Minsky of the connectionist camp. He had also an interesting personality. He was a psychologist, a biologist, a musician. He had a lot of talents. And what he built looked like this. This is the plan. It was called the perceptron. And by looking at it, you can see that it kind of looks like a neuron, right? It has multiple inputs, one output. And the way this works, you might wonder, how can this thing help us recognize images, for example? So let's say that we set out to recognize squares. What we can do is to take an image, which might or might not contain a square, and we break it down into its elements. It's pixels, we would say today. This word didn't exist back then, but actually that's what it means. A pixel stands for picture element. So it's literally that. And we send the values of these pixels to the inputs. So we just take these values numerically, we send them to the inputs. And then each pixel gets multiplied by a weight. This is the main trick of the perceptron. Each pixel has its own weight. And then they all get summed together. So what we are looking at is a weighted sum, okay? And this weighted sum then goes through a step function. That essentially means, what is the value of this weighted sum? Is it low, below a certain level? Okay, nothing happens. Essentially, this machine outputs at 0. Is it above that level? Then this machine outputs a 1. How does the machine know how to output a 1 or a 0? What is it that sets apart a perceptron that recognizes a square from another that recognizes, I don't know, circles? The threshold is actually quite arbitrary. I could pick a different threshold. Yes, I have to retune a few things, but it doesn't change much, surprisingly enough. Any other guesses? The weight, that's the thing. Those are the parameters, right? You are right that the threshold is also, that was actually coming, but the main difference is the weight. So different weights, different purposes for this machine. So the problem becomes, how do I find the right weights to recognize, I don't know, squares? And because what I want to do is something like this, right? I send it a square, I get a 1. And the way that it does recognize squares was the main intuition that Rosenblatt and the connectionists had. It works by example. Essentially, it learns by looking at many examples. I would collect many examples of squares and something that is not a square. There are a handful here. I would connect thousands of examples or more. And I label them with 1 or 0, depending on this is a square, this is not a square, okay? And then what I do is I take all these images and I send them to a perceptron that has random weights, right? Or maybe all the weights are 0. In any case, it doesn't matter. Some value for the weights, and then what I get is garbage, because this thing is essentially producing random values. So some of them are the expected values, the green values. Some of them are not the expected values. It's random. But then there is an algorithm that I can use to maximize the amount of right answers that I get. So after passing this algorithm through the data, I'm essentially tuning the perceptron to the examples. So I get the right values, maybe not all the right values, hopefully many of them. And the idea is that after doing this, hopefully, this perceptron can take something that might or might not be a square. I don't even know whether it's a square or not, and it will give me Pretty accurate, pretty reliable, hopefully. Answer about is this a square or not. Probably better or much better than random chance. This phase where I tune the machine based on example is called the training phase, by the way. So you might think, come on, it's a weighted sum. It's not going, it doesn't even know what a square is. It's kind of surprising that it works, but it does. You can try it for yourself. You can download, for example, one of the most popular benchmarks for computer vision, which is the MNIST database. It's a database of handwritten digits. It contains 60,000 digits. Here are a few just to show you that this is the real thing. It's properly hard to read handwritten digits. And then you can write or download the code in any language to implement a perceptron and train it on this data. This is the code that I wrote. It's Ruby. I am aware that it's unreadable here. The point is not reading it. It's just showing you that it's not much code. It's a perceptron. It's not a Rosenblatt perceptron. I used a few more modern tricks to, speed up training and the like, but it's pretty much that thing. And what I got was surprising accuracy. This snippet of Ruby recognizes handwritten digits with over 90% accuracy, which was, to me, it was very surprising the first time I witnessed this. And of course, Rosenblatt didn't have this luxury of using Ruby or any other higher level programming language. So what he did was he built hardware to implement the perceptron. It looked like this. Then you complain about spaghetti code, but these are just the connections of the inputs of the camera to the weights, the pixels to the weights, okay? And then the weights themselves were potentiometers that were rotated during training with electrical motor. The entire thing, of course, took the entire room. It was a monster, but also an amazing machine. And it was pretty good. It got results. So that was the situation. Oh, you were taking a picture. Come on. That was the situation in the 50s. It was symbolists versus connectionists, or maybe Minsky versus Rosenblatt, if you wish. Okay, so the big academic authority and the outsider, who, by the way, got money from the US Navy to build the perceptron. And this went on for a while, and they were both, prone to make promises, sometimes, honestly, extravagant promises. They were both prone to hype, to be frank. Maybe Rosenblatt was a bit worse in this respect. There is this article from the New York Times after a press conference with him. And, sorry. So he was saying, hey, this thing is going to stand up soon and, give a speech and reproduce itself. Be conscious, boom. So, yeah, people believed that because, of course, computers, they looked like magic to the broad public. And Minsky, he was completely livid. He was jealous, right? Because this guy was wasting perfectly good research money on a stupid idea that couldn't go anywhere. He got most of the research money, honestly, but he had so little hope in the perceptron leading anywhere that he didn't want to see a single cent wasted on this silliness. He had studied perceptrons, actually, in his youth, so he knew a thing or two about them. And in 1969, Minsky decided to move in for the kill. He decided he had enough of this stupid connectionism thing, and he set out to settle the matter once and for all. And he did it the way academic people often do. He wrote a book. It was this book. It was a book about perceptrons, which, of course, was not to praise this idea. It was actually to show the limitations of this idea in a very formal, very mathematical way that left no space for misunderstanding. And what he showed, I will come up with a less mathematical, more modern example. Let's say that we have a perceptron, and we want to use this perceptron to predict whether a Netflix series will be renewed for a new season based on two parameters: the number of viewers and the ratings on, for example, Metacritic. Okay? And we collect data. And let's say that this data looks like this. Okay? Blue stuff gets renewed because it had a lot of viewers or high ratings or both, and green stuff does not get renewed. So the question is, can a perceptron learn this data, learn this pattern, and use it to predict reliably whether a series will be successful or not? And the answer is yes. And the reason why I'm so confident in that is that this data is what a mathematician would call linearly separable, which means that you could trace a line like this to separate these two clusters very neatly. Okay? All the blue points on one side, all the green points on the other, and in this case it's a line because this is bidimensional data. If you add one more input variable, then it would be the equivalent of a line with one more dimension. That would be a plane. With even more dimensions, it would be a hyperplane. Now we cannot draw it anymore. But in every case, it would be a straight shape. That's linearly separable. The technical term is a linear shape, of course. So in this case, a perceptron can identify this straight decision boundary. It's a decision boundary because then it can use it to decide whether a specific point that we give it afterwards is in the blue camp or the green camp. Okay? But the problem with this is that the real world is messy. It's not this clean. Come on, these data are fake, right? And nobody thought that they were real data. You don't expect this cleanliness. You expect something a little bit more messy, maybe like these, two clouds of points that intersect, they would probably overlap. So you can still learn patterns from this data, even if very, very twisty. And gnarly, but what you wouldn't expect is to separate them with a linear shape. You can't. And in fact, a perceptron confronted with this data cannot do much but find a linear shape that kind of separates most green things from most blue things. And yeah, this is better than nothing. It's probably better than random chance. And apparently, it's good enough to get 90% on MNIST. But if I have anything that is more complicated than MNIST, or if I want more, sensibly more than 90%, I'm out of luck. A perceptron cannot give me that. It just can't. So that's what Minsky said. He said, look, yeah, it's cute. It cannot go very far. There is the real world. There are real problems, and this thing cannot solve them. Actually, there was a twist in this. Minsky knew, and the connectionists knew, that there was a theoretical way to extend the perceptron to find carved decision boundaries and deal with non-linearly separable data. That is, if you take a second perceptron, and you connect the output of the first to the input of the second, if you smash them together like this multi-layer perceptron that results can indeed deal with nonlinear data. It can deal potentially with any data. It can find any tortuously carved decision boundary. But the problem is that nobody knew how to train this thing. That is, there was no neat algorithm to say, hey, here are the examples, let's tune the weights. And Minsky thought that such an algorithm was impossible, that it would never be found. So he was like, okay, so the perceptron by itself doesn't do much. Multi-layer perceptrons would, but cannot be trained. Let's write the whole thing off and stop this. And focus on what really matters, which is symbolic AI. By the way, these days, we usually don't call this thing a multi-layer perceptron anymore. We have another name for it. So that's what Minsky wrote in his book. It worked a breeze, like a breeze. The book was super successful. Suddenly, nobody cared about connectionism anymore. Research money dried up. People stopped looking at perceptrons altogether. The public was very disappointed. The entire thing kind of disappeared. And a couple of years after that, Rosenblatt died in a sailboating accident. And that really looked like the end of it. So it had been a good idea, but it was destined to be forgotten. Except that it wasn't really, because there were people who kept doing this. It was like, they were like the medieval monks, keeping this thing alive in the darkest night of the Middle Age. And I'm pretty sure that it's almost inescapable. One day we'll get a crappy Hollywood movie about these people. Because they just, everybody was against them. They were a handful of people who believed in something. And the academic mainstream was like, yeah, sure, neural networks. And they just kept going. They took 40 years. They solved every problem, one after the other. Like in the 70s, they found finally an algorithm to train neural networks, the algorithm that Minsky didn't believe could ever be found. It was called backpropagation. And then they found that neural networks that were built by smashing together two perceptrons were okay, but to get really powerful networks, you had to add more perceptrons, to train more of them, so you needed more layers. But training deep networks with many layers was super hard for a number of reasons, so they tackled all those reasons, which were mostly to do with numerical computation, and they could build deeper and deeper networks. And now they got deeper networks, but they were so slow to train that it was pretty pointless to just experiment with them. And then two external things happened that really boosted them. One was neural networks are mostly, the computation inside them is not very hard. It's simple computations, but on very, very big matrices. And CPUs really suck at doing that. And they were stuck with that until the hardware companies started producing computers that could do matrix operations on very large matrices and do them really fast. They did it to solve another problem that is also all about big matrices, and that's computer graphics, in particular video games. GPUs. And that's when they got the hardware. The connectionists got the hardware that allowed them to go really fast at these experiments. Besides playing Quake, they started using GPUs to train neural networks. And another thing that happened was that neural networks are super hungry for data. The deeper they are, the more data they need to be trained. And nobody had that much data in the 90s. But then the internet happened. And then Google and Facebook amassed huge amounts of data and started hiring neural network researchers. And it all came together at one point. If this were a Hollywood movie, there would be a moment where the hero, stands up and everybody is like, oh, he's the hero, and people, I don't know, claps their hands. And And that happened in 2012 at the ImageNet competition. This was a competition for computer vision. It had been dominated that far by symbolic AI programs. And those programs were not doing too good, honestly. They were pretty bad. But then in 2012, a bunch of researchers entered a deep neural network into the competition. It was called AlexNet. And AlexNet didn't just win. It wiped the floor with the competitors. It was doing like 40% fewer mistakes than the second competitor. So at that point, everybody had to pay attention. Suddenly, neural networks were not just a fringe, weird thing for freaks. They were the thing, okay? Except that most people, or at least many of them, didn't really want to use the term neural network because they had been the butt of the joke for so long. They wanted a term that didn't have that much baggage, so they found a new term. Frank Rosenblatt couldn't know because he had died at sea 40 years before that. I'm pretty sure he would have been really delighted to see his ideas vindicated like that. Marvin Minsky died in 2014. He was still a very respected academic figure. He still didn't like neural networks. And I guess there must be some kind of morale, right? Some kind of, uplifting lesson we can take for this story, like, oh, good ideas always win, and da-da-da. And I actually looked for it, to be honest. I wanted to close this talk like, oh, you see. But then I started considering it seriously, and I was like, wait a minute, because it's insincere, because we don't know where this thing is going, because it's big. For the first time in history, we have machines that can beat us at our own game, right? They do typically human things better than humans, like vision, image recognition. So we can, of course, they're going to make our life better, drive our cars, and help us with medical diagnosis. But also, they are creating an entirely new category of problems. Weird Black Mirror problems like, mass snooping and privacy violations and killer robots. And it's kind of creepy, in fact. Don't tell Alexa I find her creepy. She probably already knows that's part of the problem. So no morale here, okay? Because if you look down the road, it kind of makes your head spin, and I really don't know where this thing is going. But this was the story of how it all began. Thank you. It's okay. Sure.
Questions?
You can take a picture of this. This is going to the printers soon. The code is going to... Andy Hunt sent me this, I don't know how long, February 22. I didn't leave any question open. I didn't leave any stone unturned. Thank you.
Thank you very much.